7th webinar in the series of the SESAR Digital Academy. We are going to have a session this time on the future vision and the technological innovations on CNS. Last time we did a session on the holistic view, so the overview basically on the CNS on the roadmap and the spectrum aspects, and we're still elaborating a bit further into that, so we'll go back into the details of the topics that we're addressing today in a moment. Just to recall for those that are listening in that the number of presentations that we did were the ATM master plan, the higher levels of automation, on machine learning, artificial intelligence. We had 2 sessions on virtualization, remote tower, and the virtual center. And we will still have 2 more themes this year, one on the use-based consolidated research results on the 12th of November. It's not yet posted on our website, but it will be very, very shortly. And then 3 sessions on smart and sustainable solutions for greener ATM, dedicated to the airport aspects, the climate descent, so the TMA, and to en route, which we are still preparing, but we intend to still broadcast those as well later this year. Know that all our webinars that have been done have been recorded. They are publicly available on our website. If you go to events on the SESAR website, you'll find them under past events. You can also find them on YouTube, and that includes on our website also the presentations and the questions and answers. The same will happen for this session. It's going to be recorded. It will be publicly available afterwards. On your screen, on the right side, for the audience here, you can see a couple of tabs. So the chat, questions, polls, and people. So if you want to know who else is listening in, you can look at the people's tab. I guess most of you have already found the chat. I see lots of people saying hi. Hi, everyone. And then the important part for interacting with this panel is the questions tab. So if during or at the end of all the presentations you have any questions that you would like to have to be addressed during the questions and answers, feel free to put them in there. The speakers already have the opportunity to answer them online, but we will still go through as much as we can at the end of the time until we run out of time. So don't put your questions in the chat, because we're not looking at the chat. So only the questions in the questions tab, please. So then, today's speakers, we have Juan Manuel from Indra, on the ground-based to space-based. Then we have Christoph Riacek from Frequentis, from single function to integrated CNS. We have Radek Saruba from Honeywell, on the evolution towards digital voice. And we have Bill Holtzman from IFATCA, from barometric to geometric altimetry. And you may have noticed that exceptionally, we're actually organizing this webinar in the afternoon. Most of them have been done in the morning. That is because Bill is actually broadcasting from the US. And we really appreciate to have you here in this webinar, Bill. So thanks for joining. I will introduce each speaker separately just before they do their presentations. And we'll start with Juan Manuel. So let's see, we make you a bit bigger. So Juan Manuel Cibrian is an aerospace systems engineer in Indra, involved in satellite communication activities in the frame of the European Space Agency national defense programs since many years ago. He was the project and technical manager of the ESA IRIS Antares project for the design of the SATCOM system for ATM, and he's also involved in the follow-on activities of the IRIS service evolution and the SESAR SATCOM-related solutions. He has been the technical leader of the ESA study for the cost-benefit analysis of SATCOM for air traffic management, and he's currently participating in SESAR 2020 Project 14 on the communication solutions for the future communications infrastructure, the multi-link future SATCOM and hyperconnected ATM, and in Indra activities dealing with satellite CNS systems. Juan Manuel, the floor is yours.
Thank you, Ruben. Can you hear me correctly? Okay. So thank you very much, Ruben, for the introduction, and thank you for giving me the opportunity to give this presentation, which is from ground-based to space-based. The idea of this presentation can be seen in this first slide, in which we have the concerning CNS services, we have the three domains: communications, navigation, and surveillance. And those domains started, of course, with the use of ground infrastructure, as shown here, showed currently in the slide. So for communications, the VHF analog voice, the VDL mode 2 data links, the high frequency systems, and for navigation, the classical navigation systems, ILS, DME, and surveillance, the radars, primary, secondary surveillance radars, the multilateration or wide area multilateration. So those systems are well-established ground infrastructure, but they are normally covering ground. They are normally covering continental and most populated areas. So in this sense, space-based systems, satellite systems, are already from a long time ago used to provide those CNS systems. For example, it's clear, known to everybody that navigation is very much based on constellations, of MEO constellations, starting with GPS and Galileo, GLONASS, etc. And also satellite communications from a long time ago. There are satellite communications providing mobile services, of course, to aeronautical services, as shown here. More recently, there has been also systems providing surveillance, global surveillance, SDSB, which are already operating and is a step forward for surveillance in this sense. And then finally, in the future, it is seen that all those systems will be part of an integrated CNS systems, and in the cases communications will be composed of the future communications infrastructure and in a multi-link concept. Okay. So, as I mentioned, the first step for a system, satellite system to provide CNS services is the GPS. GPS is, which started with military applications, but then was opened to other applications, in particular to aeronautical ones. From the 19th, it was certified and is widely used. Okay. Then later it came the other constellations, Galileo, Video, GLONASS, and all those services. All these navigation systems is not strictly dedicated to ATM. It's dedicated to a wide range of applications, as shown in the figure. No? Not only aeronautical, also fleet management, there is vessels, etc. So plenty of applications are widely using the navigation constellations. So as a second step, this is the Inmarsat system. Inmarsat system is in operation since a long time ago. Providing global mobile communications services through geostationary satellites. And in particular, these services are not only aeronautical or maritime, aeronautical and different services, but in the case of aeronautical, there is the classic aero system, which is in operation since the 90s. It has been in operation 25 years, or around 25 years, and has evolved to the currently used Swiss broadband safety services. This SBS services system has been constructed over the BGAN, which offers a broad range of services, and is commercially in operation since 2018, but really was being used before, okay, long before. This system will evolve, as we know, as is research in SESAR in this line, that will be part of the multi-link concept and also introducing the future IPS. Okay, so applications where we know that is providing ATS the data services, voice, and AOS services. So in this slide, what I want to show is the overall satellite constellation and systems that are already providing CNS services. So here we have the three constellations, GEO, MEO, and LEO. They are different, they have different characteristics, but all of them are providing services that are very much important for the ATM community. Okay, so starting with the upper part of the slide, there is the geostationary orbit. We have communications in Marsat and navigation, augmentation system based on those satellites. And this is the main characteristics are the satellites are big. They have a weight really big, 4,000 to 6,000, more or less, but the constellation is small. Then going to the middle, there are the MEOs, which are the navigation constellations. And in this sense, the satellites are in the middle. No, there are a wide range of possibilities here. Orbits from 3,000 to 30,000 kilometers, or weights from 700 to 1,500 kilograms, and a number of satellites around 30. And then we go down to the last constellation I'm presenting, which is the LEO ones, okay, which now is really a trend to deploying plenty of them. In this slide, I show the one that is Iridium, that is providing already CNS services, that is using relatively big satellites, around 900 kilos, and constellations are much bigger, and there are plenty of different constellations. So specifically, Iridium has done a evolution, important evolution lately, going from the Iridium, the old one, to this Iridium Next. And an important thing here is, in addition to the communication services, safety voice and data services that is providing, is also a payload from Iron is providing for the first time coverage in surveillance. Surveillance for the remote areas, for the poles, and so is a global surveillance service available. Okay. I also want to note that this system is relatively complex. It's implementing inter-satellite links, which is really very efficient to provide good performance in latency, for example. So what's the trend? So as I commented, the trend is that there is an explosion of proposal for deploying LEO constellations for different applications, and this is generally named as the new space. Okay, what is the new space of? What is consisting of this new space? So one thing is that there are lately many new companies dedicated to launching, okay, in the market, which is meaning higher competition, is meaning that prices of launching is reducing. Okay, is for example SpaceX or PLD, which is a small company in Spain, and this translated in that an explosion of a number of launches in the late years. In the graphic in the right, which is from a forum that was done in Spain, Spanish Small Satellite International Forum, there was this graph showing the evolution of satellites that are launched from 2000 more or less, and you can see that from 2014-15 there has been an explosion. There are some announced ones, and there are predictions that very high. This is just to know that this was presented before the pandemic, so probably this will be not a little later, of course, and we will see. But in fact, there are really a provision of many launches for SE. So this new space is also based on small satellites, CubeSat style. Okay, that a good thing is that they are using a standard. They are standardized. This standardization makes easier the integration of components, of elements, and they are at different sizes. There are 1U ones, but there are 16Us, different sizes standardized. And the masses are also very wide range, from 1 kilo to several tens of kilos, 50, 60, etc. There are plenty of different configurations. And the fact that this is standardized facilitates the integration of technologies, of new technologies, being able to use codes equipment, okay, being able to adapt to the evolution of the technology. In addition, as the satellites cost less, it's maybe starting to be cost effective to dedicate the constellations to specific applications. For example, it could be ATM, but there is also other constellations that are dedicated to Internet of Things, for example. that are being launched today. So this is becoming more feasible. And these satellites normally has a short lifespan, which means that you have to replace a shorter period of time with respect to geo satellites. Okay, but in the other sense, this allows to update them technologically, to put on board new technologies as they are appearing. Okay. An example of a Leo constellation is this one. We selected this one from SPAR, okay, which is called the Lemur 2 constellation. This is not an ATM constellation, but it's providing services like meteo services, like for maritime AIS, okay, services. And it's really impressive because it's using 4 kilos satellites only. Okay, and with this, it's able to provide the mentioned services. And in addition, some of the satellites are including receivers, ADS-B receivers. Okay, so we probably the trend in this satellation is that to exploit this service too. Okay. What are the benefits we see for this type of systems? As I commented before, due to this the lower satellite manufacturing and launching cost, and due to the short lifespan that allows a faster deployment of new technologies, this can be really adapted and provide specific services. Okay, specific services very well adapted to fulfill the requirements. For example, these constellations could make use of new terrestrial or ground standards, communication standards, and be use them from also from satellite. Okay, as is the last part, I include several aspects that are interesting to be supported by them. For example, as I commented before, surveillance services. Okay, surveillance services are possible to be supported by by this type of constellations. In addition, there is the possibility that PHF data and voice can be supported also from those satellite constellations, making use of the same equipment that is on board the aircrafts today. So this can make easier the deployment of those systems. And to note that, for example, in the SALSA project, they recommend that in addition to ADS-B, those systems could provide VHF voice to try to approach performance in oceanic to continental ones. Okay, there is also important to note that in the World Radio Conference 19, there was already studies launched to study this possibility, the allocation of VHF band to these services. There are initiatives already. I think you know that the Singapore that is presenting in ICAO, okay, voice. This is also an initiative for Indra, recently presented, to provide this type of services. This as a final conclusion and compilation of the main points I present in this slide, how can be the future of CNS systems to provide ATM, okay? So we see that all those systems will be part of this evolution of towards an integrated CNS system, and this integrated CNS system will be able to support future ATM applications, future requirements. For example, in case of satellites, of course, they are providing globality including poles. They are providing communications, navigation, and surveillance, and will be probably primary in oceanic and complementary in continental. And navigation, it is clear that GNS constellations, all of them will be part of a very high performance navigation systems, okay, complemented with augmentation based on geosatellites. And also, there is also research in a trend towards a dual frequency multi-constellation that at the end will provide automatic launching, automatic takeoff, okay? In surveillance, it is clear that surveillance with a step forward in global LDSB, we have that ATM world has now global surveillance that will be consolidated in the future, and maybe there will be more surveillance systems that can also be based on space systems, okay, like wide area augmentation, or maybe even video from satellites could be a possibility. And finally, communications. As communication systems, we see that there will be several communication systems that will be will compose a future communication infrastructure. All those systems working in a multi-link concept, and this will be applicable both in all globally, that is continentally and in oceanic. And so there will be the geo satellites, so the current LEO satellites that are evolving, that are supporting a broad portfolio of services, not only ATM, but passengers, but maritime, many systems, but also including safety services at very high performances. And this will be also complemented with new LEO constellations, maybe ATM focused, and taking advantage of their specific characteristics for the lower latency and global coverage. And I think this is my last slide. So thank you for your attention.
Thank you very much, Juan Manuel. I found that extremely useful to see this overview of what is all possible already in this place. You made a very nice bridge towards the next presentation by mentioning integrated systems from a space perspective, and then for the oceanic as primary means and terrestrial as a backup. And that actually introduces very well the next speaker, which is Christoph Riak, who is going to talk on the integrated CNS, so from moving from dedicated C, N, or S functions towards more integrated technology. So let me see. Can you take down your presentation, please? Thanks. Then, Christoph. So, Christoph, after graduation from Vienna University of the Technical Vienna University, Christoph started to work for Frequentis in January 1999. Since 2000, he's working as the Frequentis project manager, and since then, more than 10 years, he's working in the research area of future communication solutions in the aeronautical domain. He has been involved in the development of LDACs since the early stages. For Wave 1, so that is SESAR 2020, Wave 1, which is the first R&D wave that we had under the new framework of Horizon 2020, Christoph Riacek led the solution on the development of the FCI, so Future Communication Infrastructure, terrestrial data link, which was successfully completed by the end of 2019. Currently, he's involved with the follow-up project aiming to carry out the necessary activities to allowing LDACs to reach TRL6, so technology readiness level 6, by the end of Wave 2. Christoph, the floor is yours.
Thank you, Ruben. Good afternoon, everybody. As already mentioned, my talk is about from single function to integrated CNS, and I'm basing this statement on LDACs. And for that reason, because I'm pretty sure that not everyone knows exactly what LDACs is, I've structured my talk as follows. I will first give you some key facts about LDACs, and then explain how LDACs can be initially deployed. And then the main topic of the talk is how LDACs, which is primarily a communication system, can be extended towards navigation and surveillance capabilities. And finally, I give a brief overview about the status of LDACs, how far we are, what are the next steps, and so on. So, what is actually LDACs? LDACs is an acronym which stands for L-band Digital Aeronautical Communication System. And LDACs is the upcoming broadband and secure terrestrial communication system for aviation. When we started to design the LDACs in 2008, it was always the aim to exclusively design it for aviation use in the protected aeronautical L-band with RMRS allocation. What is meant with that statement is that in the beginning, we had a research project where we analyzed an approach to use the gaps between existing systems in the VHF band, but later it was decided not to use the VHF band, but the L band to deploy such a system. And in the World Radio Conference 2007, the L-band was also adopted, or it was endorsed to use the L-band, which is normally only used for navigation systems, also for the LDEX, and that is meant here with the EMRS allocation. In one of the previous slides of Juan Manuel, he already explained the so-called FCI, the Future Communication Infrastructure, which is currently developed within the SESAR program. It's an IP-based infrastructure which should serve the future new concepts developed, operational concepts developed within SESAR. And one of the links, the data links included in the future communication infrastructure is LDAX. It's the terrestrial data link, but we have also the satellite-based component and also a component which is mainly dedicated for usage at airports. It's the Aeromax data link. LDAX is already a mature technology. We already started the standardization activities in ICAO under the communication panel, and it's also very well reflected in ICAO's global air navigation plan. What does LDAX offer? LDAX provides broadband connectivity to enable modern ATM concepts. As I said, LDAX was really developed from scratch, and it's really intended to be used in the aeronautical domain for secure and safety or safe exchange of aeronautical applications. And therefore, we used the modern technologies which were available at that time. That was LTE and 4G. So LDAX is an OFDM system, and it provides a very high data rate, which is 55 to 260 times higher than VDL Mode 2, which is the currently in use data link. And why there are two different figures, the 550 kilobits per second and the 2.6 megabits per second, is due to the fact that the interference situation in the L-band has to be taken into consideration when selecting the coding and modulation scheme. At the very beginning, of course, there's very high interference, so we have to have a very robust coding, and therefore the data rate is lower at the beginning. But if the interference situation gets better in the future, if some of the systems will be removed, then we can also use different coding rates, like, for example, 64 QAM, and then we can achieve higher throughput. Additionally, LDAX also provides improved communication performance to overcome current deficiencies. For example, LDAX is not only a data link, which is used for communication, but it also provides additional functionalities, like, for example, digital voice, or it can also accommodate for air-to-air communication. Initially, LDAX needs, as I said, it's a terrestrial system. It needs support from ground, so it needs a ground station. But there's also a feature implemented which allows for direct communication between aircraft. Furthermore, LDAX provides for low latency transmission through coordinated channel access. That's different to the currently available VDL Mode 2, because here we have CSMA access, where a lot of collisions are occurring. In LDAX, we have a dedicated channel, and so you can fully sure that every 240 milliseconds you have access to the channel, and you can send data from the aircraft to the ground. Then we have also implemented selective service priorities for safety critical ATS and AOC services. This would mean there are quality of services available to ensure that the higher priority services are transmitted first. And this guarantees that the safety critical ATS services can be sent. And a very important feature here is because LDAX will be implemented in the future communication infrastructure, which is IP-based. So cybersecurity is always a very important topic here. And LDAX has implemented all the security features. For example, only to name one, is that before you can access LDAX, you have first to authenticate, and only if the aircraft has been authenticated and is known to the ground station and to the whole network, then you can get access to the ground station. And finally, I already said it, LDAX is really designed to close the capacity gap we have at the moment, because currently there are a lot of new services developed and operational concepts within SESAR, and with the currently available data link, it's not possible to introduce these services. So LDAX not only covers the existing baselines 1 and 2, but also the emerging baseline 3 and all the additional services which are currently developed, for example, the full 4T TPO or flight-centric ATM. And LDAX is a really integrated CNS system, because it not only exhibits communication capabilities, but also navigation and positioning through ranging to ground stations, providing enhanced APNT capabilities. I will later explain what this means. And it can also support surveillance through the detection of LDAX transmission at ground stations. Here I have to admit that communication is the primary means for LDAX. It will reach a very high TRL at the end of 2022, TL6, and also navigation has a very high TRL, TL4, whereas surveillance is only backed up by paperwork, and it's more on a research level than the two other functionalities. So maybe that's also interesting for you how LDAX can be deployed, because it's a new system. Therefore, it's always important to think about how a new system can be put into the field. And the most important requirement here is to reuse existing infrastructure on board and on ground as far as possible to reduce cost. And the idea here is to combine technological advantages of LDAX with the existing VDL Mode 2 infrastructure, and to develop a combined multi-mode VDL and LDAX radio, which can then be brought into the avionics box on board. That would mean there is no additional antenna and no additional avionics box required. The idea is to exchange the VHF antenna with a multi-mode antenna, L-band and VHF, and also the VDL and the LDAX radio should have the same size and form and function as the single VDL radio. And the advantages then here are, you can use LDAX wherever a ground infrastructure on ground is available. So in very high dense traffic areas in continental Europe, it's very likely that LDAX will be deployed first. And here you can also then use LDAX from the very beginning. Then it's meant to be gradually introduced. And as I said, it will probably be introduced in these regions where there is the highest demand for additional bandwidth. And the use and return of investment already starts with the first LDAX ground installation. So it's a clear rollout concept how LDAX can be deployed. And having said a lot now about LDAX, I would like to put this into the context and how it relates to the CNS transformation, because LDAX is used as a showcase or use case for the integrated CNS, but everyone knows, okay, frequency spectrum is a finite and limited resource. Availability of necessary protected radio spectrum is critically prerequisite for implementation of new ATM systems. And this was already mentioned in one of our previous CNS webinars from one of our Eurocontrol colleagues. There is a growing demand from non-aviation users to use aviation spectrum, and therefore it's of utmost importance that radio frequency for aviation is used more efficiently. And this is the idea for the integrated CNS, and to integrate everything into one system. And LDAX can support this idea. It's a communication system. It already proves that navigation is working fine. This was also validated via flight trials. And there are also some concepts available how LDAX can also support surveillance functionality. The screenshot here shows where LDAX will be deployed in the L-band. The reverse link, which is the link from the aircraft to the ground, will be in the lower part, whereas the forward link will be in the upper part of the L-band. So how we can do the navigation. Here it's important that navigation functionality and also surveillance functionality is only a secondary means in case the primary means, which is currently DME or in future GNS, will fail. LDAX can here act as an additional sensor for the APNT, the alternative positioning and timing. And it works as follows, because here LDAX ground stations are continuously transmitting on the forward link, and then the ground stations can be seen as pseudolights in the combination of pseudo and satellites. And if the ground stations are perfectly synchronized and you can see in the scanning mode at least 3 or better 4 ground stations, then the aircraft can evaluate the pseudo ranges and can do an offline calculation of the position. That's one possibility to use LDAX for navigation, and another possibility is to use LDAX for surveillance. Here more ideas, but I only focused on the ADS-B. As I said, LDAX has a dedicated channel. Every 240 milliseconds, you can use this channel. In this channel, you can downlink whatever data you would like. In ADS-B case, you can use the data received from an external means like the GPS and send this data down to the LDAX ground station. It's better than currently available because LDAX ground aircraft have to be authenticated, and therefore you are sure that the data transmitted is reliable. And another possibility would be if you deploy more ground stations, not only the ground stations which are needed for communication, then you can also use LDAX as LDAX-based multilateration system. But as I said, this has lower readiness level than communication and navigation. So finally, what is the current status of LDAX? LDAX design is already completed and technical specifications are available and published. Demonstrate the equipment has been manufactured by several vendors like Frequentis, Rohde & Schwarz, Leonardo. Flight trials have already been conducted in 2019, and we demonstrated that the navigation and communication functionality with all the security features worked. Then LDAX is well established in ICAO's Global Air Navigation Plan and SESAR's ATM Master Plan. And as already mentioned, ICAO standardization was initiated in September 2016. Draft SAPs are already available and are currently validated. LDAX manual is currently developed, and the plan is to have the standards available from 2024 onwards. So that was mainly everything I wanted to say here on that topic. For your convenience, I compiled another slide where I put together all the key points. The most important thing I would like to emphasize once again is that LDAX offers an excellent opportunity for extension towards navigation and surveillance. Of course, only a secondary means in case the primary system fails. Okay, thank you.
Thank you, Christoph. I noticed that we are definitely targeting an expert level audience here. The questions, I can hardly keep up with just ordering them at the moment. So there's so many coming in, which is good, but it means that you're all going to have a challenge in preparing yourself for the question and answers sessions. Thank you very much, Christoph. Can you take down your presentation, please? So that's, yeah. So the next speaker is Radek Zaruba. I think, well, you'll clearly explain in a moment, in a bit. But you're going to present on the evolution towards digital voice. There is a bit of a connection to, I think, both the previous presentations on the space-based and on the LDAC's capabilities of voice over IP. But I'll leave it to you. So, to introduce you, during his 15+ years at Honeywell, Radek has worked as a system engineer on a number of research and development projects, including navigation, surveillance, and communication radio technologies. For the last 8 years, he focused primarily on the safety-critical SATCOM and data link services for ATM being developed under the ESA, IRIS, and SESAR programs. Radek also actively participates in the related EuroK, RTCA, and ICAO standardization working groups. Radek, the floor is yours.
Okay, thanks, Ruben, for the introduction. You might have noticed actually that Ruben didn't mention any expertise on voice, and now I'm going to present evolution towards digital voice. And to be honest, I don't really consider myself an expert for digital voice, and the reason I'm here probably is that I was just brave enough to get volunteered for this kind of presentation. By that, I want to say that there are certainly many people that know much more about digital voice technology, like voice over IP, about the digital voice ground infrastructure. There are probably also people who know more about SATCOM digital voice, even though I have some background there. And there are also people who know much more about the operational use of voice for ATM. But there are probably no experts on this planet that know everything about both those aspects, about like the operational use and the underlying technologies. And what I'm trying to do with this presentation, what I'm trying to explain here in this presentation, what I'm trying to achieve is actually try to maybe a little bit better scope or narrow down or focus the discussion on what digital voice actually means in the context of ATM and what we as the whole industry eventually need to do to evolve or maybe decide not to evolve, or what should we do with respect to the future of digital voice in the ATM concept. So as I said, digital voice means very different things to different people, depending on whether they are coming from the operational world, so typically controllers and Earth space planners, or whether they are coming sort of bottom up from the different technologies, like myself coming from SATCOM or Christoph coming from LDACs. So we all have very different views on what digital voice actually means. So as I said, I will not give you any statements like this is what digital voice will look like in the future. I'm more going to pose questions and explain why I think those questions eventually need to be answered. So first, a little bit about motivation. Why are we actually talking about digital voice here? And why do we think that eventually the evolution towards digital voice may become useful or necessary? So first of all, we are running out of VHF spectrum. So this issue has had a lot of attention over the last number of years, but primarily with respect to, at least within the SESAR environment and etc. But so primarily got the attention due to the problems we are having with VDL mode to data link. So we know that we don't have enough channels for VDL mode to data link. It causes all the issues with ATM deployment, etc. So, but the issue with VHF is also for the plain old analog VHF voice. So what I understood is that if we would have more frequencies at VHF, so more voice channels, we could open new sectors and rearrange the airspace to be more efficient. So that's really blocking even the old analog VHF voice. The other potential benefits are that with digital voice, you can have a number of useful features which are difficult or impossible to put in place with the analog VHF voice which we have today. And I will get back to it a bit more on some of the following slides. But there are also some myths that are associated to digital voice. And we won't have time to debunk or to explain and go to details on all of them. So I just listed some key aspects here which we came across over recent discussions we had within SESAR. So first, like many people say, and it's true to some extent, that digital voice is spectrally more efficient than VHF analog voice. So yes, it indeed is true, but only in some specific cases. It depends on how do you want to use voice. And again, I will touch on that a little bit on the following slides. The other reason maybe is that people thought that it's really strictly needed for virtual centers. So virtual center is the concept where controllers from different parts of Europe or different parts of the world can actually support if there is a lack of controllers in completely different region, so they can remotely connect to the local voice systems and assist the overload controllers within certain airspace. So it really allows you to control airspace which is remote from you, and you can dynamically change from sitting in one room and one location on the Earth. You can control different airspace areas in different countries even potentially. So yes, it's true that you need some digital voice there, but primarily on the ground segment. So you need to be able to connect to different radio stations on the ground, depending on which sector you need to control. And similarly, there is the notion that we strictly need digital voice for fly-centric operations. So again, like you can handle even these concepts with VHF with some limitations. So obviously, digital voice could bring some benefits there, but it's not strictly needed. So now going to what I said at the very beginning of my presentation, that there are like those different perspectives, like completely different views on what digital voice and how could it be used. So first, I'll try to interpret the operational view on how could digital voice be used for ATM. And I just try to group it into two potential use cases or two potential scenarios. So the first option is to use it for point-to-point telephone calls. So it's like myself calling my sister or my wife, just make point-to-point call. We agree on whatever we want to agree on, and then we drop the call. So similarly, controller can call selected aircraft. They agree on some clearance or conflict resolution. Once it's done, they drop the call. That's how the SATCOM voice is used today. Today, SAT voice is used typically still over via a radio operator. So it means that the pilots and controllers are not calling directly each other, but they call radio operator. The radio operator issues, communicates whatever needs to be communicated, and then gets back to the controller or the pilot to conclude the communication. So this is now moving towards direct control to pilot communication. So pilots or controllers can make direct calls to aircraft, even for the standard communication. But this concept where you make those point-to-point calls are not matching what's currently foreseen for the operational concepts in the continental airspace. Right, so imagine that you want to issue clearance to an aircraft. You need to dial the aircraft, wait until the call gets connected, then issue the clearance, and then drop the call. So that's not what's foreseen for the continental airspace. So what we would essentially need is something like teleconferencing, something similar to what we are doing right now, right? So multiple aircraft join a teleconferencing room, and they can communicate with each other practically in real time, like having a conversation within the teleconferencing room. And then depending on what ATM concept should this support, it could be like one teleconferencing room per sector, or one teleconferencing room per air traffic controller, or per something else, depending on what the concept would be. In some transition periods, we could also have some VHF-like solutions. So something that would really give you the look and feel of today's VHF. So you wouldn't be tuning VHF frequencies, but when switching from one sector to another, from one controller to another, but it could give you all the push-to-talk broadcast, always-on communication experience like VHF. So this could be another use case. And with digital voice, it would give you those. I talked about the potential benefits. It could give you some of those benefits, like seamless handovers from one controller to another, so you wouldn't have to ask pilots to tune to different frequency. So you could probably find solutions, find some use cases for having the aircraft automatically handed over from one controller to another. So this is the operational view. How could you actually use the digital voice from the operational perspective? But then, like engineers like myself, maybe Christoph, maybe some others come from the bottom-up perspective and saying what's really possible with the digital technologies. And there it gets really difficult. So telephone calls, that's what exists today with SAT voice, right? We are operationally using, and it's digital voice, but it's digital, so circuit switch or packet switch, voice over IP is one of the digital technologies. It's not the only technology, but even that's being put in place now. So point-to-point telephone calls are being used today operationally in procedural airspace. If we would want to use it that way, even in continental airspace, that would mean to reproduce the same similar technology in the new on the other future communication infrastructure links like LDACs or maybe some other future satellite constellation. With this, as I mentioned before, with this concept, what we see as critical, or what we perceive, what we know is critical, is the call setup time. So that's what I mentioned before. You want to issue clearance, and you don't want to wait 30 seconds until your call gets connected. You want to get connected practically immediately, right? But so we said that this is, so from technical perspective, this is possible. This is relatively straightforward to do, but it's not corresponding to what we need operationally. So what we need operationally is more like teleconferencing, and that's really tricky, because if we want the teleconferencing to give that like always on experience, so the aircraft takes off, gets connected to a teleconferencing room, stays connected all the time, can have real-time conversations, that gets really demanding. Either we need a lot of bandwidth, so imagine like people sitting in one room, they can either talk directly to each other, which would need like whatever, some 8 kilohertz of the audio bandwidth, and that's what VHF is doing, or everybody in the room would get connected over their cell phones to the local base station. Then that would very likely consume notably more bandwidth, because each of those calls would actually reserve its own bandwidth, both in the uplink and downlink direction. So it wouldn't be more efficient in the end if you have many people joining the same teleconferencing room, unless you implement some really high optimization down to the physical area of the radios. It's not impossible. It's just not the way the systems are being typically designed, and it's very challenging. So there really is a big challenge on making these teleconferencing systems efficient down to the radio spectrum. Is there anything else I want to mention here? Yeah, so I just mentioned that with the spectrum efficiency, there really is no such solution in the systems being currently used for aviation or being planned to be used, or that are planned to be used. There are some studies and there are some technologies in 4G and 5G. So this shouldn't read 4F on the second bullet from the bottom, it should read 4G and 5G. They seem to focus on uplink only, and so it will be like from the control to the aircraft, but you still have the issue on the other direction. So multiple aircraft talking to one controller. And then if we would want some like dynamic teleconferencing, where you want to quickly pull in different aircraft to one teleconferencing room and then drop them away to save spectrum, then again, the call setup time would become critical and would get close to telephone calls. So I have just 2 pictures just to illustrate this a little bit. The first one is representing the standard point-to-point telephone calls, where you may have 2 aircraft on the left-hand side. The aircraft may have different radios. I'm showing SATCOM, LDACs, Aeromax, VHF here. And you can see the difference between SATCOM and LDACs and Aeromax, so digital systems, and the analog VHF voice. So analog VHF voice, when pilots and tuned to certain frequency, they all share those 8.3 kilohertz of frequency, and they just have a conversation within 8.3 kilohertz. But with SATCOM, and presumably if LDACs and Aeromax would support voice, it would be the standard solution there. If you dial a call, if you get a connection from the aircraft to the ground, so then each of those aircraft actually reserves its own channel on the air-ground link. That's why the spectrum efficiency is sort of a myth with the standard digital systems. You could still use this telephone calls to dial into a teleconference. So you could still get connected to Zoom or WebEx or even this teleconference via today's SATCOM system, but it would be very inefficient on the air-ground interface, right? Whereas if you would want to have really the teleconferencing as sort of standard use, then you would need to go down to the physical layer of the systems, link layer, and all through all the protocol layers, and come up with some highly tailored solution that would allow you to do the same thing we are doing with VHF. So all the aircraft would be sharing the same physical channel in the uplink and downlink direction, and that's not impossible, but it's major challenge, really. Okay, then this was focusing, what I just talked about was focused on the air-ground link, but we also have the ground-ground infrastructure, and there actually we are using digital voice already today. So we use voice over IP between VHF ground station and air traffic control center, or between air traffic control center and the aeronautical station, so the radio operator, which then uses SATCOM or VHF voice, or we can, with a direct controller to pilot communication, we use digital voice infrastructure between the ATC and the satellite service providers. That infrastructure used to be PSTN. Now it's migrating towards voice over IP-based ground infrastructure, but it's really ground only. So if I go to the previous slide, it's really from the ATC to some voice gateways on the ground. And then there is another different digital technology used for the air-to-ground calls, or that air-to-ground is analog VHF. If we would want to go to the teleconferencing systems, then first we would need to deploy the actual teleconferencing services, like we have WebEx, Teams, Zoom. Now we have this, I'm not even sure how the system we are using right now is called. So you need to have somebody to deploy, certify, and develop these kind of services for safety critical operations for ATN. Plus, you would need to do all that I was talking about before with the optimization of the air-ground link so that they can efficiently support this kind of teleconferencing. And it's a big challenge. So as I said at the beginning, I'm not really going to give any like statements or any guidance on this is what's going to happen. But what I thought I would conclude with is to just phrase a couple of questions which I think need to be answered, or which should be addressed in the coming years probably. And again, from operational and technical perspective. So from operational perspective, what we really need as a, like I'm speaking now on behalf of the engineers developing the technical enablers, what we need to understand is which concept, operational concept for the use of digital voice is the most useful or most desirable. Is it like the telephone calls? Probably not. Is it teleconferencing? Then what kind of teleconferencing? Is it like always on? Is it like how big groups of users? You know, in what kind of regional constraints? We also need to understand how will the new digital voice eventually combine with the existing VHF voice. And eventually also important, very important, is to understand like what level of independency we need between voice and data. Then we need to understand what parameters, if we go with the teleconferencing probably or calls, telephone calls, what are the critical parameters from operational perspective? I mentioned call setup time, voice latency is probably also important, but how important it really is more questionable. And what's the acceptable latency on the conversation? Is the always on capability or always how critical, so that we have all the aircraft always connected and constantly hearing each other? What will be the number of users, etc. And then there are also, I mentioned those extra digital features that can be enabled by digital voice. So like, you know, selective muting and caller ID, so you can know who is talking, just, you know, you can authenticate callers, etc. So things which you can do with your WebEx and other teleconferencing systems today. And then the most important question, perhaps in the end, is how much are we willing to pay for those different features? So if we say, like, we really want to move to this new concept and use some of those new features, how much are we willing to pay for that? And there are two options, as always. Like, either we invest a lot into development and research and come up with some highly optimized system that will allow us to do that always on and be at the same time be spectrally efficient. And that will require like a lot of investment into research and development. Or we just accept that we will pay a lot for the operational costs. We won't have that many users using these new technologies, or it won't be like everybody always using it. And then we could just maybe have some tailoring of the existing telephony systems, air-to-ground telephony systems, and just use those. But then the actual costs for the operational costs would be much higher. And then the other direction, technical, bottom-up, we need to, as technical solution providers, we need to define, evaluate, and then down select the candidates that would meet the operational requirements, and then obviously develop, validate, and deploy those winning solutions. And this will be obviously iterative process between the technical and operational perspectives. And eventually, in the end, we would come up with one solution that would help us mitigate what I talked about at the beginning, so the lack of VHF frequencies, and allow us to deploy some new ATM concepts. Okay, I'm done. I hope I didn't exceed my allocated time slot. Please not much.
Thank you very much, Radek. That was really appreciated, and thanks for having the guts to step up. I know that was a difficult topic to bridge from operational requirements, needs towards a very technical story that you're telling here. I really appreciate that you also touched upon the multi-link connection, even though this was now in the context of the voice. In fact, that is also what we're building in the context of data link. And I think we'll probably touch a bit upon that when we go into the questions and answers on resilience. Just for information to the audience, I have invited one of my colleagues, Olivia Nunes, who is backing us up in this case and taking over, answering, let's say, a couple of the operational questions, which I think, looking at the time, we are already running quite behind at the moment. So I think that what we're going to do is focus on just a few key topics in the questions and answers, which are more on the technical side. We will look at the other stuff. So, but if it's really tailored operational, I see them already being answered online. Whatever is not answered, we'll answer afterwards. Bill, you're next. So, as I would say, the big exception in this panel, you actually have an operational background, and as the other exception, you're non-European. I just want to again really thank you for being just volunteering to be here and give your presentation. I think before I read your bio, what I just would like to recap is that in all our webinars, we have a mixture of maturity levels of solutions and objectives that we're presenting here. So sometimes we just present some exploratory research or fundamental research, so which is more on the academic side. I think the majority of the work that we've been presenting over the last webinars is focusing on industrial research. So that is prior to doing the actual disindustrialization, validating that the ideas that initially came out from exploratory research are actually going to bring the benefits in terms of safety, capacity, environment, etc. that we're looking for. And some is actually just presenting ideas of future research that we hope that we will be able to address at some point. So the material that Bill is going to present, even though there's plenty of links to work that we're doing, is not from SESAR. I would like to emphasize here that Bill has a background has been working for the FAA and is speaking with the knowledge of IFATCA in general. So the topic that he presents is from barometric to geometric altimetry. So Bill Holtzman retired from controlling air traffic in 2015. I'll just make it big for a moment, so that everyone can see who you are. Having spent his whole career as an area controller in the region around Washington, D.C. During his career, he was quite active with the American Controller Union, NATCA, and made a number of contributions in software development and air traffic procedures. He also represented NATCA on the IFATCA Technical and Operational Committee for 6 years and continues to participate in IFATCA today. Since 2016, Bill has been working for a small government contractor providing analytics, software design, and ATC subject matter knowledge to projects involving trajectory-based operations, ATM maintenance, FIXM, trajectory modeling, and the enhancement of the FAA's core radar processing and display system HERO. Now that's a lot. You're going to focus very much on one specific topic. I give you the floor.
Okay, thanks, Ruben. Can you hear me? And does the presentation look adequate?
Yes.
Okay, wonderful. Okay, so good afternoon, good morning, and good evening. I see there are people from all over the world, and it's great to be able to collaborate this way. I'm going to talk about geometric altimetry. Let me define first geometric altitude. It's the altitude of an aircraft as measured from mean sea level. Okay, sounds pretty simple, right? Today's barometric altimeters try to measure geometric altitude, but they're really quite imprecise. Barometric altimetry has been the bedrock of aviation since Jimmy Doolittle flew the first blind flight in 1929 in New York. The revolutionary barometric altimeter used in that flight was built by Paul Colesman. This device, which some still use today, contains a wafer that expands and contracts with external air pressure. These changes turn a rod that makes the needles in the gauge turn. The device is nothing more than a pressure sensor calibrated to show altitude. It's a beautiful instrument, but it's 91 years old. In today's demanding high altitude, high performance, and high precision environment, the use of barometric altimetry is a major hassle. We don't realize it because we're so accustomed to using it, and we've never had an alternative. These are some of the issues with it, and I'm going to discuss each one. Since it really measures air pressure, the barometric altimeter must assume a specific correlation between pressure and altitude, the standard atmosphere. As you see, pressure changes less at high altitudes, and barometric altimetry loses its precision. So that's why vertical separation standard is 2,000 feet above 410. The same 2,000-foot standard existed above flight level 280 before RVSM. Methods of ensuring altimeter accuracy are required in RVSM, however, including the regular monitoring of performance from ground-based height measuring units, HMUs. Maintenance and use of HMUs are a significant resource burden in the support structure of barometric altimetry. This graph shows how an HMU identified issues with an aircraft's pressure sensors. It's only the religious but costly monitoring of altimeters that makes RVSM possible. As you know, aircraft below the transition altitude require a local altimeter setting. The infrastructure needed to support the hourly measurement and dissemination of this data costs a lot of money to operate, especially since a small error can result in controlled flight into terrain. There's also a drain on radio frequency time by controllers issuing the settings individually to each pilot. A further safety issue involves aircraft passing each other but using different altimeter settings because they're in contact with different controllers. Altimeter setting errors by pilots are as easy as turning a dial too far or transposing a digit, but they can be catastrophic. Tiny objects and organisms can literally destroy the integrity of the barometric altimeter. The safety of the aircraft rests on these little holes, remaining clear of debris, paint, bugs, and dirt, as well as the avoidance of any distortions in the 50 to 500 knot airflow sweeping past. In 1996, Aero Peru Flight 603, a 757 from Miami to Santiago, Chile, crashed, killing all 70 people aboard. The air data computers were unable to show correct airspeed and altitude on cockpit displays because a maintenance worker had failed to remove tape covering the static ports on the aircraft exterior. Pilots must inspect their aircraft with incessant and tireless vigilance. Aircraft designers must also exercise tremendous vigilance and effort to ensure that the static ports measuring ambient pressure on the outside of an aircraft are not affected by the attitude of the aircraft or any other condition. This is so critical that during the transition to RVSM, some aircraft had to be reskinned to be compliant, and others were simply retired. Deviations from standard atmosphere will result in errors proportional to that deviation. According to ICAO Doc 8168, an approximate correction is 4% height increase for every 10 degrees Celsius below standard temperature. This is safe for temperatures above minus 15 degrees, but for colder temperatures, a more accurate correction should be obtained, according to the guidance provided in section 4.3. When temperature is less than standard, an aircraft will be lower than the altimeter reading. When the surface-based atmospheric pressure in the local area drops below standard, then the lowest usable flight level is raised. Otherwise, someone flying above the transition layer could be closer than 1,000 feet to aircraft flying below it. The transition layer is simply the space in between and varies in geometric depth from country to country. Up to 1,500 feet of altitude can be marked as a transition layer in many nations, and additional space can be lost as a function of the altimeter setting. These represent wasted space in our altitude structures. Today's aircraft in the flight levels follow isobars of pressure, which means the geometric altitude of the aircraft. The distance from the mean sea level to the aircraft actually changes with local pressure. With respect to the Earth and the geometric altitude, aircraft climb and descend while in traditional level flight. Some feel this puts additional wear on engines since the aircraft experiences uphill and downhill segments, like a car driving on hilly roads. Even with the help of height monitoring units and all the efforts that go into design and maintenance of aircraft fuselages and static ports, the accepted tolerance range for altimeters is still 240 feet. That means that standard separation can exist and two aircraft can pass each other with just 510 feet between them. An A380 is about 80 feet tall, So the difference between two aircraft can be as low as 430 feet. So this brings us to the question of why do we use 1,000 feet to begin with? This standard is almost as old as barometric altimeter. In today's world, the standard has been back engineered using collision modeling and probabilities, but in its day, it was basically a safe guess. It's easy to say, it's easy to understand, and provides large buffers. 245 feet of error is a massive percentage of the total relative to modern tolerances. What if we could find a more precise way to measure height and reduce that? Even a small reduction would provide a number of new altitudes, just as happened with RVSM. Anything other than 1,000 feet would cost an enormous amount of frequency time and wildly increase the chance of a readback error, as long as we still use voice for clearances and express altitude in feet. But could we not label the new altitudes with simple terms, such as level Alpha 1 or level Bravo 2? The experience of transitioning to RVSM and RVSM environments taught us all the tremendous value of increasing the precision of lateral and vertical measurement. Throughput in high altitude sectors soared with RVSM. It helped barometric altimetry survive, but when will it be time to finally replace this antiquated technology? A lot of statistical studies have been done to justify it, but recently the SESAR R-Wake project found that 500-foot separation would work if only altimetry could be made more accurate. This leads us to the question of what is the alternative? This is one of the reasons we're still using pressure-based altitude. There really haven't been any, but there is one today. Positioning satellites can be used for the determination of geometric altitude. ANSPs who collect MODIS data have had access to this for over a decade. Aircraft report their position based on satellite signals, as we all know, and they can also report their altitude based on satellite signals. Global Navigation Satellite Systems, or GNSS, are satellite systems used for terrestrial navigation. GPS is one, for example. Galileo is another. GNSS-based altimetry is the measurement of geometric altitude using GNSS. Can we use it today? Well, we do already. Terrain awareness and warning systems compute an estimated average altitude using pressure and GPS altitudes. GNSS landing systems use satellite signals to create a virtual ILS path. The ADS-B out message can include GNSS-based altitude and vertical rate. The ICAO Separation and Airspace Safety Panel strongly encourages the use of GNSS-based altitude by ADS-B to replace the previously mentioned height monitoring unit, which is limited in range to 40 nautical miles. Paragliders use GPS altitude in competitions, and Google Loon balloons operating above 50,000 feet provide internet to remote areas and report GNSS-based altitude. Our world is moving towards trajectory-based operations, meaning providing the aircraft with the ability to choose customized climb and descent paths. In the graphic, the green trajectory is the ideal, the idle engines all the way down to landing, and the red is the traditional descent path. Barometric altimetry is not a friend of these methods because of its imprecision. The potential energy of the aircraft in cruise, and therefore the optimum descent profile, depends on geometric height, not pressure-derived height. But is satellite-based altimetry ready for more? Well, no, it's not. There are a number of reasons why, and here's a short list. Position determination requires 4 or more satellites in view. It is calculated based on the time required for a radio signal to reach the receiver from each satellite. But the determination of satellite-based altitude is more problematic and depends on having not only enough satellites in view, but also having some lower angles in the sky. Receiver Autonomous Integrity Monitoring, RAIM, is a GPS technology in which the aircraft performs self-contained fault detection of satellite data. But RAIM only supports lateral navigation, not vertical. The vertical accuracy of a GNSS-based receiver is typically 50% worse than horizontal accuracy. Satellite-based augmentation systems such as the US WAAS and the European EGNOS use a network of ground stations to collect GNSS satellite data, determine corrections, and broadcast these to users. These provide more precise position determination, and the same is true in the vertical dimension. WAAS enables vertical performance to nearly match performance in the horizontal plane. So satellite augmentation enables vertical integrity using today's GNSS. And as you see, at the as of September 10th, 2020, there were 4,064 LPV approaches, which are completely satellite-based approaches in the U.S., with 1,191 of them at non-ILS airports. So it's replacing ILS. The original GPS used just one frequency for civilian applications, L1. As you can see, other constellations use additional frequencies, and this diversity can provide protection against interference. Satellite-based augmentation systems are regional, not global. For a global solution to improving vertical integrity, additional GNSS constellations are needed. With a second constellation of adequate coverage, advanced RAIM is possible with vertical guidance for precision approaches. Newer GPS satellites are equipped to provide frequency diversity with L5 and L2C signals. Next generation of US GPS will be more resilient, more accurate, and more available, and is in the process of construction and should be operational in just a few years. By using additional frequencies, GPS gains an important advantage that gives its signals diversity and protection against interference. We're all aware of what's going on below 400 feet. There are billions of dollars being invested in low-level operations to move packages and passengers and to monitor and inspect activities on the ground. There are all kinds of plans for this airspace, and it has been recognized that new methods will be needed to be developed to keep these vehicles separated. At the heart of any separation management system is knowing where each vehicle is and its altitude. When you have only 400 feet to work with, an error of 245 feet isn't going to get you much capacity. It would be like working a high altitude sector that only owns 1.5 altitudes, say from 30 to 315. You can't even change the altitude of one aircraft without using someone else's airspace. The point is that development of low-level drone traffic is going to force the development of new methods of measuring altitude. Most concepts for both low-level and high-altitude drone integration involve both segregated and integrated airspace. Drone vehicles seem likely to require some form of geometric altitude, given the ineffectiveness of pressure-based altimetry. This seems likely to lead to a mixed mode of operation, which has always been more difficult and introduces risks. Most low-level deconfliction concepts, including the German Aerospace Center and SESAR, involve automated deconfliction of drone trajectories similar to what is depicted here by the FAA. But what must be noted is the resolution between the trajectories in this graphic. It's not clear that anyone has really defined how this precise resolution is to be established. Geometric altimetry is likely to be required to manage the coming deluge of high-altitude vehicles, including all of those shown here. There are many reasons for vehicles to cruise above 50,000 feet, including communications and internet provisions, surface observation, operations support, research, and passenger travel. Air traffic control itself could benefit immensely by the presence of high-altitude, long-endurance vehicles that can process position reports and communications. You know, we talked earlier about satellite communications and satellite surveillance, but there are lags involved with that. If you can use what's known as an atmospheric satellite, which is a high-altitude, long-endurance vehicle of some kind, those lag times could be greatly reduced. You know, imagine oceanic traffic communicating position and voice through an airborne network with very little lag time. There's no question these technologies are coming in large quantities to our skies. But with dwindling performance with altitude, barometric altimeters simply aren't up to the task. Just as in the low-level drone use case, high-altitude operations are going to drive the use of satellite-based altimetry. This will enable the reduction of separation minima and more efficient use of airspace. It's not going to happen today or tomorrow or next year or even 5 years, but it will happen and will be a good thing for air traffic management and aviation. Our community needs more precise measurement of altitude with more automation. Satellite altimetry will eventually be a no-brainer. Pressure-based altimetry is ultimately a crude method with all kinds of workarounds, corrections, validations, and maintenance that are labor-intensive and costly. The explosion of drones in the sky will drive the need for a reliable, automated, and precise means of measuring altitude that will use satellite signals. But any transition will be a monumental undertaking as it involves virtually every aircraft in the world. Making that transition will take a generation, and a lot of resources and energies will be needed simply to create the foundation for that evolution. It would be best to start that work today. Thank you, Ruben.
Thanks, Bill. Very much appreciated. Can you take down your presentation? We are all back in the panel. Thanks. Also, that presentation for me, it was really very clear to understand, to be explained what the issues are with our current barometric and even the safety issues that we have. If you compare them against let's say the reliability concerns that may exist with the GNSS-based altitude precision and reliability. There is a lot more to say on it, and I'm hoping that at some point we're going to have some research to look at this in more detail, because I do think there's a lot of potential there. We are definitely running a bit out of time. We have officially 9 minutes left. I intend to go on a bit longer, so for the people that are not able to listen in for a bit longer, know that this webinar is going to be recorded. It's going to be published afterwards, so you can even listen to the last bit of the debate that you may miss if you have to step out in 9 minutes. Having said that, I've been looking at all the questions and answers that came in and tried to group them a bit together. I decided that for time purposes that the technology-specific questions I'm going to leave for the offline answering. So the answers will be published later on. I'm going to focus here more on the topics which are more interesting for a debate within the panel. So in particular, those topics are related to safety certification, to resilience and cyber. Oh, that's my dog. Sorry. And on the business case and the avionics and environments. I think I saw a couple of questions passing by on UAS UTM. I think I'm going to refer to the next webinar. There is going to be a next webinar, in particular on the consolidated results for U-Space. So I would trust that those questions will be addressed there. We'll still look at it offline. So let's start with the safety and certification. And I think there are two questions that I'm going to start with for John Manuel, which are from Michel Carandente and Claude Pichavant on something which was not well received, let's say, as Iridium not being a ATM focused. But I did see your answer already, but maybe you can elaborate a bit on that.
Yes, thank you, Ruben. Yes, maybe this has been misunderstood. We were referring that Iridium is not only providing ATM safety services, it's providing many services. It's providing mobile communications, general purpose, for passengers, for many things. And in addition to that is, of course, providing safety services which are certified, so are really safety of life services. But their performance are the ones that are expected in this sense.
Okay. I'm going to stick a bit with the safety and the certification. So we'll probably move on to connected to the second topic that I have prepared here, which is on resilience and cyber. But so I think what I see in the audience is that there are quite a couple of people that feel, let's say, not at ease with moving from a ground-based infrastructure to a space-based, with the idea that it is not as reliable, that it's not ready for safety critical applications. Especially since we're now broadening that up. We're looking into serving multiple functions, not only our positioning that we have here already, but also communication and surveillance. So how do you look at that? And what is the role of EASA and certification? How do we build a safety case in this new innovative environment?
Okay, this is a good question. Okay. In fact, our vision is that the EASA has its framework, let's say, that you have to fulfill. So these new constellations, these new systems has to be able to fulfill those requirements. They are designed, if they are ATM focused, for example, they will be designed with this in mind. So as the current satellite systems, for example, they are doing, and this will imply constraints. It will imply features that you have to support, and it will imply a process. And this is what you have to be aware when going to these type of solutions.
Okay, so I think what is also important to know is that the one of the what is it, the Aeron service is actually already EASA certified. So it is actually already used for separation purposes over the ocean.
Exactly. Okay. Yeah.
I'm gonna take the next link to resilience. So resilience is very much related to safety, I would say. So it's not anymore necessarily you, John Manuel, answering. It's maybe also a question for Radek and for Christoph. So whoever wants to speak up, feel free to speak up. The question here is, there are again a couple of questions related to it. If we try to move towards, let's say, integrated CNS, so for example, on Christoph, you presented that on LDACs, which may actually serve as well for alternative positioning and maybe even for surveillance at some point. Yeah. Now, if we're moving, so either on the ground to integrated LDACs, for example, integrated CNS, or on the space side, how do we still ensure resilience with backup systems? What is your views on that? Who wants to start?
Yeah, as I said, for the LDACs, it was always mentioned or meant that not everything will be integrated into one system, because then you have really troubles with the safety case. And therefore it was intended, or LDACs is intended to be only a secondary system for navigation and surveillance in case the primary system will fail. So this would mean, for example, if the GPS has an outage, then maybe you can use navigation functionality to derive the position, and use this position to send it back to the ground. But it was never meant to integrate everything into LDACs as a primary means, because then you have really problems.
Okay, thanks. Anyone else who wants to respond here?
Yeah, I would just say that it will follow the same practices like we've been always following in aerospace, right? So you will always need to prove that if there is certain hazard levels associated to failure of one of these C, N, or S functions, you may need some level of independency. So where you can't really integrate everything into one system, if there's like common point of failure, which would make your C and N and S all go down at the same time, just through the single point of failure, your safety analysis would point to that and would not allow you to do it that way, actually. So I think it's just the standard practice that needs to be followed always in all new deployments. And you always need to show that it's only getting better with the new technologies, which is sometimes tricky because you don't know what the performance of the old technologies is, but you always need to follow the same practices to show that the systems are not getting less reliable with either the more integration you do or the more new types of technologies that you introduce.
Okay, I guess that's also why, for example, we are working on the multi-frequency and multi-constellation positioning for GBOS approaches, for example. So moving from GAST D to GAST F to increase the reliability, less sensitive to ionospheric disruptions, and definitely less sensitive to constellation outages. So even when it's space-based, there could actually be multiple service providers there. Juan, you want to add anything on that before we move on to the next?
Yes, basically I have the same view that Christopher and Radek. So because sometimes when you are talking about these functionalities, this cross-domain functionalities of one technology supporting several domains, it seems contradictory, because as says Radek, then you end up in a single point of failure. But this is not the idea, as they commented. So the idea is to have additional means to support the resilience and the requirements. So in fact, what you end up with a more robust system, really. With a system integrating these things means that you have a more robust system and you handle in an integrated way, let's say.
Okay. Still, last topic on the last question on the resilience. We actually touched upon it in the previous webinar in the presentation from Aquari, which is related to cyber. In the technologies and the evolutions that you've been presenting, so on LDACs, on digital voice, on satellite functions, how do you see that we will address in the future that it will be resilient or robust enough against cyber attacks? Who wants to start?
Well, that was something that I try to address. The use of different frequencies, gives you redundancy and some defense against cyber attacks. But I mean, I think if someone's determined to jam a signal, I mean, I'm not sure how you would actually prevent that. You just need some kind of a backup plan.
I guess indeed that it's independent of whether your service is digital based or analog based. In all cases, you can just jam a spectrum, a frequency, I guess.
Yeah, I guess with cyber, always the defense against denial of service type of attacks is always difficult to impossible if you have radio links involved like this. You can try to make them more resilient towards jamming effects, but you will never make it 100% robust. So I think we just need to learn how to live with that risk. And the same thing with any existing radio systems, right? So I think the bigger threat is the type of attacks like spoofing and integrity attacks where you can try to inject fake messages, false clearances, etc. in the case of communication. That's the real danger, and that needs to be protected with like strong authentication, etc. So you can't really protect 100% against denial of service on any single system which involves radio. Being in navigation, communication, or surveillance, so you can always jam those. So what you need to make sure is that you have backup plans for that, as Bill pointed out. And for the other types of attacks, it's a lot about strong authentication and firewalling and barriers put in place so that preventing unauthorized entry into the system.
Okay, thanks. Let's go into the next question. I saw a couple of questions on the geometric. I don't know if you had a chance to have a look at those already, Bill. But I think what I would like to zoom in on is a question. I think Olivia already was typing an answer there, but it's on the reduction of separation. So a question like, it cannot possibly be just the accuracy or the reliability of the altitude positioning that is the blocking factor in reducing separation. Can you elaborate a bit on that? What other factors would we need to consider here?
In terms of reducing separation, well, of course you have to consider, the wake of aircraft, and the effect that it has on other aircraft. In the U.S. and I'm sure elsewhere, en route separation has been reduced to 3 nautical miles in a lot of airspace, lower level airspace, and it's resulted in more wake turbulence incidents because now you have aircraft at cruise speed, coming closer to each other, and modeling the movement of the wake, is extremely complicated, obviously, because it depends on the winds and other atmospheric conditions. And so that really becomes a big limitation in terms of reducing the vertical separation standard. But, I think given, how large the buffers are today in the vertical domain, that, there's certainly room to narrow it down to where, you gain a lot of efficiencies.
Okay, thanks, Bill.
Mhm.
I think that's definitely sufficient for now. Before I go to the final question, so the final topic is going to be about business case, about avionics cost, about cost distribution when moving to different technologies. But before I go there, I want to just tip on one topic, which is about environment. I actually saw quite a couple of the 4 questions here that are from Paul Neering, from Laurent Jacqueline, from Ron Ogan, I see, that are all expressing concern about space debris. I guess I would need to look here at Joan Manuel. What is your idea about that? What is your view?
Yes, this is a question that is logical, no? Because as we are talking about many systems in place or many systems planned, there will be a radical increment of, let's say, devices, no, flying there. As far as I know, today and since some time ago, when you want to deploy a system, the system has to be designed, taking into account all its phases, its life phases, and the end of life is part of its life. So you have to be following recommendations and following rules to guarantee that this is will not be damaging anyone, and the end of life will be treated as it has to be. Okay.
Okay, thanks. Thanks, Juan Manuel. So now we're zooming in on business, money. In the end, it's always money making the world go round. There are a couple of questions here that are particularly focused on the cost for avionics, and I think it's Christoph, you mentioned that there may be a possibility for a reuse of existing antennas, onboard antennas. I guess you mentioned it as well, Joan Manuel, if I recall well, that for space-based VHF, we might be able to use existing VHF radios. And I think if I take it a bit more general, so it gives you a bit more freedom to expand in any way you think is relevant. When we look at moving towards new technologies that involve avionics, it's always difficult to get things synchronized between the ground and between the airborne side, with the costs for the ground and the airborne side usually being, well, let's say each one has to build their own business case, which is not always easy. And with this, also with the move towards space-based services, the whole state of the game on how service provision and service charging is going to work is very likely to be changing in the future. Do you have any views on that? I know you're all the techies here, but still, any views would be welcome.
So as I said, I'm coming from SATCOM primarily, and I think SATCOM is in like a bit easier position than, for example, LDAX, because you need SATCOM today for oceanic airspace anyway. So all the aircraft that fly in oceanic airspace do need SATCOM. So it is somewhat simpler. The aircraft that already have it installed now will have the capability to start using it in the continental airspace eventually. But it still doesn't bring us where we need. So there is still a challenge to show that to get the benefits, we need to get it deployed across also the aircraft that normally don't fly in oceanic airspace. And there are the arguments typically, and again, it's SATCOM specific, but maybe applicable to other technologies, are that it's not only for ATM. So it provides you features that you can use for other things than ATM, like your electronic fightback connectivity, maintenance data access, some AOC type of applications, either on the EFB or other aircraft systems. So I think what you need to do to be able to sell those new ideas is not to focus just, or those new technologies, not to focus just on the ATM, but if it's possible, show also some other side benefits which come from when you install that equipment on board, that it will actually bring you other features that you can use for other purposes than ATM, clearly.
Okay, thanks, Radek. Maybe there's someone who is able to answer the question. I guess it was Paco Salaper, about reuse or of existing avionics, existing antennas for different purposes. Anything you can say on that? I guess I'm looking either at Christoph or at John Manuel.
What was our idea is not to reuse actually, but to develop the new radio, which can be easily, or it's not possible to change all the cabling and to reduce the standardization and certification costs in the aircraft, to have a radio which has the same form and fit factor, and also to have only one antenna, not to need additional antennas for supporting the LDAX radio, but to use the existing, or not to use, but to change the existing antenna and to have exactly the same number of radios and the same number of antennas when LDAX will be deployed as combined radio. And the most important thing for the deployment concept we have in mind is that it's not a big bang deployment. It's rather a gradual deployment, and you can deploy some ground radios where it's required most, and then the CSPs, for example, can offer some additional services, and these additional services can be used in that regions where you need really a powerful data link, and where with the existing VDL Mode 2, these services cannot be offered. And with such additional services, like the electronic flight back, the CSPs or the ground industry can make additional benefits. So the deployment is all about to have it gradual and not one deployment for whole Europe. I think this will never work.
Ruben, I'd like to make a comment too, that if I mentioned the possibility of having these atmospheric satellites, these high altitude, long endurance drones, and if you had a string of them flying across the Atlantic, at 60,000 feet, they could serve to relay communications from oceanic traffic to back on the continent, and therefore the aircraft themselves could use their existing communications technologies.
Thanks, Bill.
Yes, Ruben, I can also add something here.
Yes, please, go ahead.
It's true that, as you commented before, that the fact that the implication to put on board aircrafts new technologies is really stopping some good technology, in fact, because it has cost consequences, as you mentioned. Yes, if you are able to use existing technology, which already is being used, and to use from a space-based system, this is really a very good key point to make this feasible. Okay, sometimes this is not so direct, but I think it's a very good idea and a promising one in which you can overcome this problem and make the deploy of the systems easier. At some moment, the technology evolves, of course, as Radek said. No, also you have to put new technology, new functions, as much as you can take advantage of what you have there on board. Somehow you can facilitate this evolution. This means technology capable to support maybe different systems or one system, or different options. Okay, but for me, the trend is that on the one hand, as much as possible, systems should be valid, let's say, for several environments, and on the other hand, technology should support to provide at the same time different systems. Okay.
Okay, thanks. Okay, I guess we need to wrap up. It looks we're 15 minutes late now. I do see more and more people disconnecting. We still have 100 people listening in, which I really appreciate. But I'm going to leave it to what it is here. I really appreciated the four of you presenting and be willing to stand up, answer the questions, knowing that quite a lot of questions are actually quite hard to answer. Also, there's still a lot of research going on. From what I take from this is that apart from just showing lots of different technologies, is that there's on the business side, we see that there are two drivers which are actually quite important to keep in mind. So it's the cost efficiency of the entire system and the spectrum efficiency of the entire system. Now, how that translates to the costs for individual stakeholders, like an airspace user, for example, I think is something that might need to be looked into, because it links a bit to the airspace architecture study and the data service provider, which has been followed up with a study from the Commission on the regulatory and economic impact of breaking down the service provision, so making some of those services more commercially services. So there is still work ongoing to understand how the impact will be such that individual stakeholders will have positive business cases when we move to a more cost-efficient and spectrum-efficient environment. I'm going to leave it to this. Thank you very much, speakers, for all your time and the lots of time that we took for preparing this webinar. Thank you, audience, for listening in. I really appreciated the tough questions and the lots of questions that we received. We will still be looking into all those questions and publish them afterwards. I wish you all a very good day.